Hi, today we're going to be talking about Module 2, Lecture 2, which is going to be talking about how to do hypothesis tests and construct confidence intervals for continuous data. So I think a good thing to do if you're confused on the last lecture is to watch this lecture, watch the next lecture, and then go back and rewatch the first lecture. And you might understand conceptually what's going on a little bit better. So we have our lecture code here. I strongly encourage you to run this code on your own after watching this lecture, step through each of the steps and see how it works. But here is our lecture slides. I've actually adjusted it a little bit, so I'm going to use mine that I'm going to load up afterwards. Okay, so hypothesis tests for confidence intervals in continuous data. So again, remember the height gain example. We have the heights of all these students. And we want to test maybe whether the average height gain or the true mean height gain is less than 2 inches versus bigger than 2 inches. That's a one-sided hypothesis test. Now recall that X bar, the sample average here, which again is a function of your data, it's a statistic, is 2.1 for this data. And we know that 2.1 is bigger than 2. So there's some evidence that the mean growth weight is bigger than 2 inches. But is there enough evidence to definitively say that mu is bigger than 2? Okay, that the mean height growth, the true height growth is bigger than 2. This is a small sample size. So all the statistics, all the hypothesis testing data that we're going to use, it takes into account the sample size here. Okay, so what I'm going to do is I'm going to test the null. Mu equals mu0. So mu0 here would be 2 versus, or that would be a one-sided test or two-sided test, or a one-sided test, H naught mu is less than mu0. So in this case, mu0 is 2. So mu0 is just a stand-in. Mu is the true population height growth. So what we do is we assume that our data, the sample that we go collect, Greg, Diane, all their heights, they follow a normal distribution with mean mu and standard deviation sigma. So these are things we don't know what they are. We don't know what the true height growth is, the average, and we don't know what the distribution is. We don't know that. But we can estimate sigma using the standard deviation, and we can test hypotheses about what the average growth is. So you don't really care as much about the spread, but just what's the general sort of trend for that growth rate. Now, assuming it comes from a normal distribution, this bell-shaped curve, I just want to point something out. There's something really powerful in statistics called the central limit theorem, which basically says that if you get a large enough sample size, your sample average does approach a normal distribution around the true mean. So this is something, if you have a large sample size and you have continuous data, a t-test is always a valid thing to do in that case. So this is the test statistic here. T is equal to the square root of the sample size of your data times X bar minus mu0, which is our hypothesized mean value. In this case, it would be 2 over S, which is the standard deviation. So if the null hypothesis is true, so in reality, the average height growth is mu0, or in the case, right, it's 2. So you knew this, God, the universe, whatever, told you. Then this test statistic, T, follows a T distribution with n minus 1 degrees of freedom. T distributions look a lot like normal distributions, right? They're these symmetric kind of bell-shaped curves. They just have higher tails. So this is just looking at, T distributions with different degrees of freedom, right? You can see with 1 degree of freedom, these kind of go down really quickly to 4. And I don't know, it's maybe kind of hard to see, but there is kind of a fatter tail as your degrees of freedom go up. So T distributions in R, you can use DT to get the density of the test statistic, and you can use PT to get the probability of observing a value smaller than or equal to that. So the probability of observing X equal to 2 from a T distribution with degrees equal 4, degrees of freedom equal 4 is 6%, so 0.06. And the probability of observing an X less than or equal to 2, given degrees of freedom equal 4, is 94%. You can also use help DT for this. You don't actually need this information. I'm just trying to walk you through what's going on with this. And then in the end, you're just going to use a function called t.test. You're not actually going to have to compute these things directly. So here's an example. We're going to read in our data first, and we'll get our mean and standard deviation because those are going to be useful. So first thing I'm going to do is check what my working directory is using getwd. I might change my working directory. I can look at the files here. Now what I actually want to do is I want to load in the height data, and the height data is in module 1, lecture 1, data set 1. Okay, so that's where you're going to go to get it. It's in that lecture material. So these are our heights. I did a header. Why do I do a header? Just to kind of get an idea of what the data looks like. I can get the mean by just taking mean of data height gain. I can get the standard deviation by taking standard deviation of data height gain. If I want to do the t-test, I'm going to take the square root of the length of the data height gain times the mean of the data height gain minus my hypothesized mean, which is 2. You can see that right here, divided by the standard deviation. My test statistic is 0.15. Now what I'm going to do here on the right is I'm plotting what does a t-distribution look like with 4 degrees of freedom. Why is it 4 degrees of freedom? Because I have 5 data points, and your test statistic, right, follows a t-distribution with n-1 degrees of freedom. So it'll have 4. So whenever I plug in these numbers, right, I end up getting 0.156. You can see this calculation down here below, but I just did it in R up here. And then I'm going to plot where my test statistic is. So if you remember things about, this is what my distribution of my test statistic should look like if the null hypothesis is true. Okay, so I just want to kind of play this through and think through it. So a bell-shaped curve, right? Most of the data falls in the middle. That's why this is raised higher. Okay, so any test statistic that's in this middle is going to be consistent with the null hypothesis being true. Anything that's way outside, maybe way out here past 4, is going to be inconsistent with the null hypothesis. Why? Because if the null hypothesis is true, then our test statistic, this red line, should follow this distribution. So it should be somewhere in the middle if the null is true. If it's false, it's going to be way outside of it. So there's definitely not enough evidence to reject this here. And I just want to point out something I did here. So this is plotting. I plot this x. This is a vector, and I'm plotting the density of this. And then AB line here, V equals T-stat, that actually draws a vertical line. You can use H2 to draw a horizontal line. And then obviously I'm changing the color just to point out the code. So if I want to get a t-test p-value, what I need to do is calculate this area. Because remember, a p-value is defined as the probability of observing a more extreme test statistic in favor of the alternative if the null is true. So if the null is true, my test statistic, right, being bigger than 0 is in favor of the alternative. My mu being bigger than 2, right? So it'd be this area right here. So as if H1 mu is bigger than 2, and as X bar increases, so does T, which favors H1, right? So you can see that here. As my X bar gets bigger and bigger and bigger past 2, my test statistic T is going to get bigger and bigger and bigger past 0. So I want to calculate this area right here, which I can do using this function here, 1 minus PT, T-stat with 4 degrees of freedom. So say I want to do a two-sided hypothesis test. Well, I can do this using H naught mu equals equal to 2 versus H naught mu is not equal to 2. I can calculate my test statistic here. I end up getting 0.12. Actually, it's 0.156. Sorry about that. And I can calculate this test statistic like this here. So it's 2 times the probability of being bigger than, it's actually 0.156. That was a mistake. So 2 times 1 minus PT, absolute value of the test statistic with 4 degrees of freedom. It's got a probability or a p-value of 0.88, which is big, right? That's consistent with the null. Big p-value means that there's a lot of evidence that the null is true. Small p-value means that there's a lot of evidence that the null is false. T-test confidence intervals. How do I get confidence intervals? I can do that in this way. This is a function, right? L, this is a function of our data. Why is it a function of our data? X bar, that's a function of our data. S, that's the standard deviation, that's a function of our data. And N, that's a function of our data, the length. This thing here, I'll talk about where we get that from on the next slide, but this is our lower bound, and this is our upper bound on the confidence interval. T star alpha over 2 df. This is the spot on the t distribution where the area to the right of it is alpha over 2. So formally, right, I've got this value here. T star alpha over 2 would be the red line if I drew a red line, where the area over here, if I'm using 0.05, is 0.025. So we can look at this here. This is my density, and this is my critical value right here. So this critical value means to the right of this line right here, we end up getting a 0.025 area in this here. So that's my critical value, we call it. So if I calculate my confidence interval, I can plug in the numbers, 2.1 minus 2.77 times 1.43, which is our standard deviation, divided by square root of 5, which is our n. This thing is 0.32, right? And then my upper bound here is 3.87. So that's my upper bound. So I can say a 95% confidence interval for the mean growth height between 7 and 8 years old is between 3.32 and 3.87. Now that also means that I'm going to reject the null hypothesis for any mu outside this range with a two-sided test. So if I want to test, do students grow at all from 7 to 8 years old? So I assume that they don't grow any. I'm going to reject that null, mu equals 0. I'm also going to reject the null that mu equals 4, or mu equals 10, or mu equals negative values. Okay, now I just want to tell you all right now, you can totally forget the first part of the lecture. You don't need to know it again for the rest of the class. That's just trying to give you some intuition behind the formulas here. All you need to use is this function here, t-test in R. So t-test in R, if you use help t-test, this will show you how to use it. By the way, why is it called students t-test? I want to let you know it's actually a pretty interesting story. So the statistician who made the t-test, his name was William Gossett. And he worked for some kind of company. I think he actually worked making beer or making beer cans, something like that. He worked in a factory. And he actually came up with the t-test while he was working there. But he didn't want to tell his company about it, because if he told his company about it, they would basically claim it and then it wouldn't be published and people wouldn't be able to use it. So he published the t-test under a pseudonym, so a false name, of student. So it's a student of statistics or whatever. So that's why it's called a student's t-test. So it's not called Gossett's t-test because he was concerned, right, that he might get fired for doing this. So this is the t-test. We're only going to focus on this first usage. The second usage is going to be used for two sample t-tests. So in this first usage, you plug in x. X is your vector of data at the top. You're going to plug in mu, which is the true value that you want to test. You can plug in an alternative here, which can either be two-sided, greater than or less, depending on what hypothesis you want to test. And then you can get a confidence interval. You'll get those values here. So simple, right? This is super simple code. You don't have to worry about anything we did before. You just have to know how to use this function, and that's it. So H0, maybe I want to test that the mean height growth is 2 inches versus it's not equal to 2 inches. Well, I'm just going to plug in t-test, data height gain, that's my x, and mu equals 2. That's my hypothesized mean. And look what I get down here. I get a lot of different things. I get a test statistic, 0.156. I get my degrees of freedom. I get my p-value. My p-value is very big, so I wouldn't reject the null. If it's less than 0.05, I would reject the null in favor of the alternative. I also get a 95% confidence interval. Very cool, right? 0.32, 0.387. Now, I didn't have to say alternative equals two-sided because this is the default here for this method. Two-sided confidence interval is the default. And I get a mean. So this confidence interval, you'll notice, does contain 2, which means I wouldn't reject that null. And it's consistent with the p-value also being large. How do I do a one-sided test? A one-sided test, maybe I want to test, is the mean 0 inches. So did a student not grow at all versus did they grow some? And so I can do this by using data height gain again. My mu is now 0. And my alternative hypothesis is that it's greater than 0. It's greater than my mu. I get a test statistic of 3.227. I get a p-value of 0.015, which is less than 0.05. So I reject the null hypothesis. in favor of concluding that students do grow from 7 to 8 years old on average. There's a true growth there. And then I also get a one-sided 95% confidence interval here. So you'll notice, right, the upper bound is infinity. When you have a upper confidence interval, a one-sided confidence interval for a greater than alternative, you're going to get an upper bound of infinity. When you have a less than alternative, you're going to get a lower bound of negative infinity. That's just how it is. Maybe I want to test, is mu bigger than 4? Okay, versus the alternative is mu less than 4. So this would be an alternative of less. So I got data height gain. I plug in mu equals 4, and my alternative is less than 4. I get a very small p-value, 0.02. So I reject the null that the height growth is bigger than 4 inches in favor of concluding it's less than 4 inches. I also get a confidence interval, one-sided, which you can see here, negative infinity to 3.46. Okay, testing assumptions. We can look at the densities of our sample to see if they're symmetric and bell-shaped. So I'll say like discrete variables are pretty problematic. So you might be familiar with like pain scores. So pain scores are measured in like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You also might be familiar with Likert scores, like how likely are you to vote for candidate X? So you might say not likely at all, somewhat likely, indifferent, likely, super likely, one of the two. So that would be a 5-point Likert scale. These are discrete variables. They are like not binary, but they're kind of granular, and t-tests don't perform that well with these. So we can do kind of a different test statistic here. It's just it's called a non-parametric version of the t-test where it doesn't assume your data is normal. If you have a large sample size, it's totally okay to use a t-test. Like a large sample size, I mean like hundreds. So this is a Wilcoxon rank sum test. It's a non-parametric version of a t-test, and it's used to test hypotheses about a median instead of a mean. So you could have the null, the median is equal to mu 0 versus the median is not equal to mu 0. So the median height gain is equal to 2 versus not equal to 2, or that the median is bigger than mu 0 versus the median is less than mu 0. It's useful for non-normal data and small sample sizes. So if you have a small sample size, I would say under 100, and by default, you should use a Wilcoxon rank sum test, sign rank test again. Okay, so if you look at it, right, this is the help menu. It actually looks pretty similar. So we have wilcox.test x. What are the arguments we can feed in? Mu is our median we want to test. We have an alternative. We can do two-sided, greater than or less than. And then we can also ask for a confidence interval. So you actually have to tell it to give you a confidence interval here. So here's an example. I'm using wilcox.test. On height gain, my mu is 2. My alternative is two-sided. And I'm saying, yes, I want a confidence interval. You say conf equals true. If you don't put this in there, it won't give you a confidence interval. So I get a p-value of 1, which is not below 0.05, so I don't reject this null. And they actually give me a confidence interval here. It's an 80% confidence interval. It's sometimes these non-parametric tests can't give you exactly a 95% confidence interval. So it is what it is. But right, we can have some kind of idea that the median lives between 0.5 and 3.99. And the median, it gives you is 2.94. You might get these errors here that there's the confidence interval level is not achievable. You also might get this error here. I don't know if you can see it, but it says cannot compute exact p-value with ties. Those are fine. It counts for these things, but it'll just spit out a warning message just to let you know. So this is what I'm testing. The median is equal to 2 versus not equal to 2. The p-value is really big. It's not below 0.05. So I failed to reject the null. I can also do a greater than confidence interval. So here I'm testing, is the median height gain less than 0 inches versus being greater than or equal to 0 inches? I can do this by plugging in the height gain, mu equals 0. Alternative equals greater, and I'm going to ask for a confidence interval. So what I end up getting is a p-value of 0.03, which is smaller than 0.05, which means I'd reject the null that the median height gain for 7 to 8-year-olds is less than or equal to 0 inches. in favor of assuming they do grow some. The median growth is some. My 95% confidence interval here is a one-sided interval from 0.5 to infinity. So again, I mentioned this before. I don't want you to worry too much about the math. I just have the math here because I take this from slides for my master's classes. So if you have a random sample that's independent and identically distributed from some distribution with a finite population mean and a variance sigma squared, then this test statistic right here, square root of n times x bar minus mu, that converges to a normal distribution, which means that you can use t-test statistics, t-tests in large sample sizes, because by default, you can have this kind of normal distributed value. And it's true in most cases. In simple terms, as your sample size gets large, so in the hundreds or the thousands, you can assume your data is approximately normal. What's large? Bigger than 30 is somewhat large, I guess, but it depends on how non-normal your data is. You can assume that 200 plus, to me at least, is safe enough to assume normality, at least if your data is continuous. Okay, so I don't mean a Likert scale data, 1, 2, 3, 4, 5. It needs to be like BMI measurements, weights, sodium levels, albumin, those kind of things. You don't need to use Wilcox tests in large data sets. And that's the end of today's lecture.